At the end of this online module, you should be able to perform axis scaling on data to identify function types of bivariate data for linear, exponential, logarithmic, or power functions, linearize data using logarithmic transformations, develop models of linearized data, and transform linearized models to rectilinear models. Let's consider a problem that will help us learn to perform nonlinear regression. Riparian buffers are the vegetated areas between land and a stream or river. They are important habitats for birds, amphibians, and other wildlife, but also serve an important water quality function. Because they are the buffer between human development, things like agricultural fields or backyards, they filter pollutants that move through the groundwater before they reach the river. While fertilizers, such as nitrogen, improve plant growth, excess amounts are sent downstream and lead to harmful algal blooms and dead zones in lake and coastal areas. To assess the effectiveness of vegetation on nitrate removal, water samples were collected from groundwater wells along the flow paths from the edge of an agricultural field to the river, on either side of the river. This is contained in a data file. As an agricultural engineer, you have been asked to model these data so that decisions can be made regarding changing the design of the riparian buffer. A quick look at the CSV file we have shows that the first column is the distance each measurement is made from the stream. The second column is for the riparian buffer with a short mowed grass. And the third column is the riparian buffer of the dense forest. Nonlinear regression is a way to represent data through equation modeling. In this course, we will cover nonlinear regression as it relates to functions that are linear or that can be linearized using logarithmic data manipulation. The following are the general form of each type of equation. When we talk about parameter identification, that means finding the values for the constants in these general forms so that the equations model the data. So how do we model data using nonlinear regression? There are 4 basic steps to modeling data. Step 1 is to decide if the data are linear or nonlinear by graphing the data on rectilinear axes, that is, a linear x and linear y scale. That will help you identify something about the shapes of the graphs. Next, if you believe that the data are not linear, you need to decide which, if any, of the 3 function types to use. Here again, we are considering exponential, logarithmic, and power functions. You do this by graphing the data on scaled axes to help verify which model to use. If one of them looks more linear and it matches what you observed in step 1, you can continue on with that function type. In step 3, you will first linearize the data. Transform the data as needed using logarithms so that the new transformed data are now linear on a rectilinear set of axes. This allows us to use linear regression on the new transformed data to find parameters for a line, which we already know how to do. Then finally in step 4, we use the slope and y-intercept of the transformed data to find the parameters of the general form of the model, so we can go back to the original data. Then, depending on what we need the model for, we will likely graph the original data with a model overlaid on it, or display the equation of the final model, or both. So this is likely not making sense yet, so let's work it out using our example problem. I recommend that you work through this problem with me. Let's begin by pulling up a script template to start us off. Also, make sure your data file is in your current folder. Begin by updating all of the information in the header. I'm going to jump forward here a bit to save a bit of time. Feel free to pause and copy this. Now we need to load our data. In the initialization section, let's use read matrix to import the CSV file called riparian_data. Don't forget the .csv. Next, let's also separate our data into separate variables for use. Feel free to pause and copy this. For now, let's only worry about modeling the data from the short mowed grass. We will revisit the dense riparian forest in a while. Okay, let's go through all 4 steps one at a time. As a reminder, step 1 is to decide if the data are linear or nonlinear. So we will plot the data on a rectilinear scale so we can look at it to see its shape. First, We will plot the data using the distance as our independent variable and the mode grass nitrate concentrations as our dependent variable. I plotted this with blue stars. I'm adding all needed information to have good technical presentation on my plot. Pause here if you want to add that to your script. Notice this AX equals GCA semicolon, and then followed by AX dot font size equals 16 semicolon. This is a set of code that will control the font size for the entire plot all at once. I will use that throughout this module in order to make my font size easier to read as it plots. Okay, save and run. Let's look at this plot. We can see that this is not linear, but does it fit one of our types of functions? Let's explore what each of these look like. Linear functions are likely the most familiar to you. If the data can be modeled by a line, we use the general form y equals mx plus b, where m is the slope and b is the y-intercept. When data look like this, we just use linear regression, so this is just a check to verify that our data are not linear. If our data can be modeled by an exponential function, the shapes are like these shown. Our general form is y equals b times 10 to the mx, or y equals b times e to the mx. When m is a positive number, the red graph represents the shape. Here you can see that b is the y-intercept and m determines the rate of growth. When m is negative, it takes the shape of the blue graph. Again, b is the y-intercept and m determines the rate of decay. Neither of these forms cross the x-axis. Logarithmic functions have this basic shape. The general form is y equals m times log base 10 of x plus b, or y equals m times the natural log of x plus b. Logarithmic functions such as these cross the x-axis but not the y-axis. Power functions have many different shapes. The general form of the equation is y equals b times x to the m. The basic shapes differ based on the value of m. When m is 1, that makes the shape a line. When m is greater than 1, the shape looks like this red one. When m is between 0 and 1, the shape looks like the purple graph. And when m is negative, the shape looks like the green graph. For all but m being negative, the power functions go through the origin. However, when m is negative, both the x and y axes act as asymptotes. With the information about the shapes of each function in mind, let's look at our plot. We can see it increases more quickly as the distance gets bigger. So this has the shape of an exponential or power equation. We can also see that it has a y-intercept somewhere between 4 and 6. So that knocks out power, which goes to the origin. So exponential is a good starting guess. So let's move on to step 2. Step 2 is to decide which of the four function types to use. We will do this by plotting the original or raw data on different types of axes using axis scaling to verify if we can use exponential, logarithmic, or power models to model our data. But what is axis scaling? Simply, axis scaling is changing the tick marks on a graph's axis to provide a different visual for the data. You already do this often. Look at this graph. I have plotted this in MATLAB, and on this scale, it looks linear. But if I use axis scaling and zoom out on the right, I can see that this is only a small section of the whole picture. There are many types of nonlinear regression. In this course, we are concerned with the types of nonlinear regression that invoke log scaling. Logarithmic scaling involves changing a number line from a linear orientation, where each unit is equidistant from the other, to a logarithmic scale, where the major tick marks represent the power of a base number. Here you can see a linear scale that goes to 100. The scale on the bottom is also to 100, but notice that the major tick marks are 0.1, 1, 10, and 100. These are equally spaced. These are the powers of 10. This type of scale is good for visualizing large ranges of data compactly and being able to see detail within each order of magnitude. Let's look at a few numbers on each scale. Notice that 100 is at the same place on both number lines. But if I want to look at 10, it is here and here. Now what if I want to note this point? On the linear scale, It could be anything from 0 to 2. But when I look at it on the log scale, it's easy to read that is actually 0.8. We will use log scales to visualize data on graphs to make determining information about the data easier. This graph contains data graphed on rectilinear scales. Again, rectilinear means linear x-axis and linear y-axis. These data have an exponential relationship. When data have an exponential relationship, if we leave the x-axis linear but change the y-axis to a log scale, the data will appear linear. Look at the y-axis here. Notice that the major tick marks are powers of 10. Notice also that the grid lines follow a logarithmic pattern as well. The values in each of these graphs are equal, but the visualization is starkly different. To get the plot on the left in MATLAB, we use the command plot. To get the semilog in y graph like this one, we use the command semilog y. Looking at the graph here, these data are logarithmic on rectilinear scales. If we use axis scaling on the x-axis to be a logarithmic scale, we get the plot on the right. Again, the left graph uses MATLAB syntax plot, but the right plot uses the MATLAB syntax of semilog x. In power relationships, we can also see these using rectilinear scales, using the plot command. But if we use log scales on both axes, we get something that appears linear. To produce this graph, we use the MATLAB syntax log-log. Okay, let's actually code this. Our goal is to plot the data on different types of axes using axis scaling to verify if we can use exponential, logarithmic, or power to model our data. We do this by making a 2x2 subplot using different axis scales for each plot. So let's make a second figure. Then we use subplot to define a 2x2 subplot and start with the first plot, which is rectilinear. This is actually the same plot we did in figure 1. So I'm going to copy and paste. Make sure to add appropriate information for technical presentation. Notice I changed the title to make it easy to differentiate between the 4 plots. To save a lot of time, let's copy and paste the first subplot and modify for the other 3 subplots. For the upper right subplot, let's change the position input to 2. For this plot, let's make it semilog in x. To change the plot from rectilinear to semilog in x, we simply replace the word plot with the MATLAB function semilog x. Remember that axis scaling does not change the original data. Therefore, in axis scaling, the units remain the same. This means we only need to change the title of the plot to reflect its difference. For the lower left subplot, let's use semilog in y. Again, change the position, this time to 3. Plot becomes semilog y, and the title changes to reflect the semilog in y axes. Finally, for the lower right subplot, we need to do log-log axes. Change your position to 4, change plot to log-log, and change the title to reflect the log-log axes. Now I want to add a title for the entire subplot. I can do this with the subtitle command. And I will give the title Nitrate Concentrations Near a Stream for Mowed Grass Riparian Buffer. Let's hit save, go to our command window and clear everything. And now let's run. Now we see that the graph with the rectilinear scale independent variable, or the x-axis, and a log scale on the dependent, or y-axis, gives us something that appears more linear than the others. As we learned previously, this indicates that we can potentially use an exponential function to model this. That also matches what we saw in our first step, where we were looking at shape. So step 3 then is to linearize the data. Linearizing data means that we will change the data from the original data, which for us were curved when plotted on rectilinear scales, to a new data set that will be linear when plotted on rectilinear scales. We do this by transforming the original data using logarithms so that we can actually use the new linear data to be able to use linear regression on it. Here is a table to help us think about the linearization process. Since we are considering exponential as our general model, let's take a look at that column. This top equation is the general form y equals b times 10 to the mx. Notice that throughout the table, it also shows the forms if you would rather use e and natural logs. For the equation modeling, our ultimate goal is to find numbers for m and b, these are the parameters, that allow this equation to model our raw original data. Looking at this equation, you can see that it is not in the form that looks like y equals mx plus b. Quickly, shifting over to the logarithmic function, you can see that it is already in a y equals mx plus b form, except where the typical x should be, you see log of x. When we go back to our exponential general form, you can see that it is not in that form. Therefore, if you wanted to linearize the equation, you could take the log of both sides. Using what we know about algebra with logarithms, this simplifies to log of y equals m times x plus log of b. So the linearized form of the exponential equation shows that if we take the log of the original y's and we use the original x's, our data will have a linear form. This is a data transformation, meaning the data are no longer the same numbers, they are linearized. That then allows us to use linear regression techniques on these new transformed linearized data. So let's try this again in our script. Since the plot from step 2 shows that the semilog graph can be modeled as linear, that means to linearize these data, we can leave the x-axis data alone because it is on a rectilinear scale. So I will make that x underscore lin, which stands for linearized x data, equal to dist underscore st. Note this step is not actually needed, but I like to do it to keep my transformation obvious. Then we also need to transform the y data. So the raw y data needs to be transformed using log. I'm going to call this y underscore lin and use log base 10 to do this. So this is log base 10 of the short underscore rip variable. Great. Now we have transformed the original data to new data that are linear. So we are ready for the second part of step 3, which is to use linear regression to find the parameters for the line of the linearized data. You can use polyfit or the regression equations to find the parameters of the line of the linearized data. I'm going to use polyfit to find these parameters. The parameters we find in this step are not the final parameters we need for our model fitting. They are the slope and the y-intercept of the linearized data. As a reminder, this is just a step in finding the parameters for the general equation of the exponential function. Okay, so now we need to finish up our general model. Step 4 results in us finding the parameters lowercase m and lowercase b of the general form of the model. Then we can decide how to show off our final model based on the context in which we are working. This table has one more row. This final row shows us how to transform your linearized slope and y-intercept, that capital M and capital B, back so that they fit our original data. Therefore, we need to get the lowercase m and the lowercase b to fit our original model. Since we are working on the exponential, let's take a look at that cell. In the linearized model, let's overlap big Y equals big M times big X plus big B. Here we see that for the variables, capital X is the same as lowercase x, and capital Y is the same as the log of lowercase y. These correspond to how we linearize the data. The parameters are now what we need to focus on. Looking at slope, we can see that the big M and the little m are both the same. But when we look at the y-intercept, the big B is equal to the log of the little b. Let's use this information to find little m and little b in our code. So step 4a is finding the parameters of the general model. From the table, we know that the slope big M is the same as the parameter little m. So m underscore model equals capital M underscore lin. Even though this isn't necessary, I still change the variable name since it helps me keep track of the transformation of the parameters. Now we also know from the table that the y-intercept big B is equal to the log of little b. If we solve for little b, which is the variable we need, we get little b equals 10 to the big B. So I will code that as b underscore model equals 10 to the b underscore lin. Make sure to continue to comment your code. Moving on to step 4b, we need to display the information in ways that make sense for our problem. I also want to visually check the fit of the model. So let's plot the original data and the model on the same plot, as well as print out the modeled equation to the screen. Since the plot of the original data is exactly what I started with in Figure 1, I'm going to copy and paste the Figure 1 code here and modify it. So the first line is fine, as I just need to plot the original data. But I need to add a hold on in order to plot the model on top. I don't have the modeled y values yet, so let's calculate these next. Remember that our general equation is y equals b times 10 to the mx. So our short riparian model equals b model times 10 to the, with the dot operator, m model times the dist underscore st. This calculates the y values for the model. So let's plot them. Plot dist underscore st for x and short rip model for y with the blue line. Let's add all of the work for the technical presentation. Again, to save time, I will just copy and paste these in. Two things to note. I added code to make my title of the plot take up 2 lines. This is done with the braces as seen here. And I need to turn the hold off. I also need to display my result to the command window, so I will use fprintf to display the short grass riparian buffer can be modeled by the following with a \n. Then follow that with the model using fprintf equals quote y equals %0.2f times 10 to the %0.2f \n end quotes, then comma b model comma m model. Okay, let's save the script. I will clear all, close all, and CLC in my command window. And I'm going to run the final script. Good, our final figure looks good and our model seems to fit well. And our equation is an exponential, y equals 4.55 times 10 to the 0.03. If you would like to practice a different type of model, you can model the data set for the dense riparian forest. To do this, start with the code we have already worked through together. Add to this code in order to display the plots and models for both the mowed grass and the dense riparian buffers on the same plot, and display both models to the command window. The following is the result you should get for the new code. In summary, this online module helped us learn to identify if data can be modeled using linear, exponential, logarithmic, or power functions using axis scaling. These are types of functions that will appear linear if we change the scale of one or both axes to logarithmic scales. We also learned to linearize data through logarithmic transformations. We do this to transform the data to a new set of data that are really linear so that we can model linearized data by finding the linear parameters using linear regression. This finds us what we called our capital M slope and our capital B y-intercept. Next, we learned to transform parameters of linear regression to parameters of the general form of the function type. That is, take our capital M and capital B that were from our linearized data and transform them back so that they are lowercase m and b parameters for our general form. Finally, we plug the lowercase m and b back into the model in order to model the original data set with the general form of a function.